This map projects 2050 demographic pressure points, identifying water scarcity zones threatening 2.4 billion urban residents. Layering ocean temperatures over that geography reveals a parallel collapse. 80% of these coastal regions intersect directly with acute coral bleaching risks. Centralized desalination is failing to meet this challenge. Running high-pressure membrane plants requires massive energy grids, which increases carbon emissions and dumps hypersaline brine back into already stressed reef systems. Securing these coastlines requires sourcing water directly from the ambient atmosphere, removing the need for marine extraction entirely. This is the premise of the Zero-Water Megacity framework, a theoretical architecture proposed by Ido Margolin and co-authored with an advanced AI. The primary hardware for this city is the Stillsuit Pi Plus, a wearable atmospheric water generator. To understand how modifying pedestrian clothing could secure a city's hydration and restore its marine ecosystem, we have to reverse engineer the design from its molecular fibers all the way up to its macroeconomic ledger. The absolute baseline constraint is physical yield. The system must extract a reliable daily volume of water per capita from the thin, semi-arid air of coastal desert nights. The foundation of the yield relies on these specially treated textile stacks, engineered for scalable atmospheric sorption directly on the human body. Woven directly into these cotton fibers is a class of crystalline materials called metal organic frameworks, specifically variants from the MOF 303 lineage. This geometric model shows the ultra-high surface area lattice. Its aluminum rod geometry acts as a molecular sponge for ambient water vapor, providing steep uptake efficiency. It continues extracting moisture even as surrounding relative humidity drops well below 30%. Capturing this vapor requires no mechanical compressors and no high-pressure pumps. Once the lattice is saturated, a mild thermal trigger is applied, achievable simply by harvesting ambient waste heat. The heat breaks the molecular bonds, forcing the framework to release the trapped vapor. Because the entire cycle is passive up until the release trigger, the total energy ceiling required to operate the wearable node sits at less than 25 watt-hours per capita per day. Within these fibrous channels, the released vapor rapidly condenses, forming usable liquid droplets that slide toward the collection bladder. This molecular efficiency permanently decouples human water survival from grid-tied coastal infrastructure. Scaling up from the fiber layer brings us to the architectural structure of the Stillsuit Pi textile stack itself. Turning a pedestrian into a water generator introduces a strict engineering tension, integrating active, resilient biological polishing processes with absolute mechanical safety controls. To manage this, the design relies on a strict logic matrix called the gray mode R delta X framework. R represents the directed noise, chaotic environmental variables the suit actively exploits, like nocturnal humidity flux. Delta is the allowed deviation window, the highly regulated internal environment where biological subsystems safely function. X is the mechanical fallback, a non-negotiable lockout state triggered instantly to protect the user if thresholds are breached. We see this applied in the suit's UTH-5 microreactor patch. Here, water flows through immobilized microbial consortia and granulated activated carbon to actively scrub impurities. To maintain the safe delta window within that reactor, a 275 nanometer UV LED plate continuously irradiates the flow, guaranteeing a log-5 reduction in bacterial load. If inline sensors detect total dissolved solids exceeding 40 parts per million, the X protocol takes over. The system physically locks out the potable bladder and diverts the flow. That diverted, non-potable supply enters Guardian mode. During an extreme 38-degree heat wave, the suit trickles this redline water across an outer wicking layer to generate active evaporative cooling for the wearer. The R delta X logic secures the hardware, turning a pedestrian into a self-contained, mathematically regulated biological node. When you connect thousands of these individual nodes, they form a community mesh, anchoring to neighborhood-scale condensation structures called fog sail hubs. But an atmospheric system has an inherent vulnerability. Weather is intermittent. Biology is not. The system must guarantee a strict 2.5 liters per capita per day, regardless of external conditions. This data topology maps the mechanism that solves that intermittency: continuous model predictive control. The matrix visually processes layered inputs, outputting a dynamic, forward-looking projection curve. The algorithm continuously digests streams of street sensor telemetry, fusing it with satellite forecasts for wind velocity and relative humidity. Simultaneously, the control matrix tracks every suit in the mesh, monitoring instantaneous yield rates, precise MOF saturation, and current bladder volumes. Using these variables, the algorithm dynamically schedules the exact moment each suit triggers its heat desorption phase, optimizing the collective yield of the entire block. If the predictive model forecasts a dry spell that would breach the daily requirement, the network preemptively routes citizens to the larger fog sale hubs to physically subsidize their personal shortfalls. By treating thousands of independent garments as a single computational array, model predictive control smooths erratic weather patterns into a reliable, city-scale utility. Securing human hydration solves only half the crisis. A coastal city cannot survive if its surrounding marine ecosystem collapses from heat stress. The city's lungs, a network of distributed reactors, use microbiome-aided mineralization to fix atmospheric carbon dioxide into calcium carbonate. This process converts captured CO2 directly into a bioavailable alkalinity cocktail. This alkaline solution is dosed directly into municipal wastewater outfalls. By elevating the pH of the discharged water, the city exports an artificial immune response to adjacent coral reefs, buffering them against acidification and heat. This gauge monitors the aragonite saturation state on the reef. The system enforces a strict gate between 2.8 and 3.2. Only when telemetry verifies safe parameters does the dosing valve open. Driving this metabolism is a cryptographic ledger called WaterCoin. Generating net positive water earns dual economic credits, one for avoided desalination and one for bound alkalinity delivered to the reef. This decentralized economy is secured entirely via zero-knowledge proofs, mathematically verifying total neighborhood liter volumes without ever extracting or exposing individual user data. Moving this from a theoretical model to execution requires a strict technology readiness roadmap. The first target, slated for 2026, aims to deploy basic moth cotton sleeves and data loggers for initial citizen science trials in physical desert conditions. This scales directly toward the 2030 objective, a fully integrated 10,000 resident pilot on the East Mediterranean coast, validated by 90 consecutive days of zero mechanical extraction. The security of the 21st century city depends on the seamless integration of material science, cryptographic verification, and ecosystem metabolism into a single functional mesh.